Everyone knows what soap is. It's one of the most common things to find in a household. Whether you're using it to clean clothes, dishes, wash your face or hands, or just take a shower. Soap is a very handy thing to have. It may seem very simple on a macroscopic level, but broken down to a microscopic level, soap is a scientific breakthrough. Soap is actually very easy to make. All it takes is a combination of alkali fatty acids and a little bit of heat to spark it. Mix it together and wait for it to cool, and voila, you have soap.
The thing that makes soap special is that it takes two key components of a molecule and merges them together. Those components would be the ability to be either hydrophobic or hydrophilic. This means that they're either attracted to water, aka hydrophilic, or they repel water or are hydrophobic. Basically, hydrophilic molecules are polar and hydrophobic molecules are nonpolar.
Now to explain what this has to do with soap. Soap can be broken down into two parts based on the prior explanation, a hydrophobic side and a hydrophilic side. The hydrophobic side consists of hydrocarbon chain that works to bring in fats and oils. The hydrophilic side consists of a carboxylate group that attracts water. Here's a visual of what the molecular structure of that would look like.
So as you can see on the left side, you have the hydrocarbon chain. That is the hydrophobic side. It's the side that rejects water. You see the little black, the big black carbon surrounded by the the small hydrogens. And then on your right side, you have the carboxylate group. That's the hydrophilic side. It attracts water. It loves water. It has the sorry, I'm a bit sick. It has the oxygen and the sodium in there, and that's, as I said before, that's the side that attracts the water.
The water reacts with the hydrophilic end of the soap via ion dipole force and hydrogen bonding. These are two different types of intermolecular forces. It lowers the water's surface temperature, which allows the creation of soapy water.
I apologize for that. What we meant was that it lowers the water's surface tension, which allows for the creation of soapy water, not surface temperature, surface tension.
The hydrophobic end behaves a little different. The hydrocarbon chains in the soap attract to each other via dispersion forces, which causes them to clump together and form a structure called micelles. These micelles are very important to the cleansing process. Inside of micelles, the carboxylate groups form a negatively charged spherical surface, while the hydrocarbon chain remains inside. The micelles remain dispersed in water because they repel each other due to the fact that they're all negatively charged. When this end of the soap mixes with oil, the hydrocarbon part of the micelles will break down the oil molecules. This leads to the formation of a new type of micelle, now with nonpolar molecules in the center. This allows fats to be caught in the micelle and they're able to get rinsed away. Here's a visual so that it's easier to explain. The fats get isolated from the water and trapped inside because of the hydrophobic carboxylates. The hydrocarbons then attract the water and surround the fats, causing them to be secured inside of the whole mechanism. This allows the fats and oils to be carried off from within the suds of soap.
Now, a question for the viewers. Based on the information given in this video, how could you make soap in your own house? This is assuming that you don't have soap for whatever reason. Hopefully, you were able to learn something from this explanation.
Tyler out.